In this example, we have another circuit here, and we see some parallel branch here. So it might be a little trickier than the previous one, still quite simple. Let's find the internal resistance R of this battery, the EMF of this source, and the current I in the circuit from the conditions given, all the other conditions given here, okay? So first of all, typically easiest to find the junction currents. Well, this current here is associated and dependent on the currents flowing in and out. This current is flowing out of this junction because this one's flowing in and this one's flowing in. So keeping that consistent. Currents leaving is I. Currents entering is 1 amp plus 2 amps. So I is 1 plus 2 is 3 amps. Now, find the internal resistance R. Let's choose, well, you got some choices. We could choose this loop here. We could choose an entire external loop. And we could go either clockwise or counterclockwise. I'm going to choose the outer loop. Looks like that. I'm going to go clockwise. All right, so let's go. So we have that the current that we already found was 3 amps. So starting here, going around, we have a drop of IR. I is 3, R is little r. Then a rise of 12 plus 12, and then minus 2 times 3 equals 0. That gives us 6 is 3R, R is 2 ohms. Now what about the EMF? Well, we need to choose another loop. I'm going to go ahead and choose the upper loop, go clockwise. I'm going to start at B in this case. I'm starting here, and as we go around this way, just add up all the potentials. So we start with a plus EMF, and then minus 1 times 1, minus 3 times 2, we already solved for the I and R, plus 12 equals 0. That gives us EMF minus 5. Well, that seems kind of weird. EMF of minus 5. Let's choose another loop for validation here. Let's choose the lower loop. I'll go clockwise again. So here it is. This time we have minus, I'm going to start at B, minus 3 times 2. And then when we encounter this one, we're going against the current. So it's a rise in potential, plus 1 times 1. And then minus EMF is equal to 0. What does EMF resolve into there? Minus 5 again. That is the solution for EMF. So both cases, we have EMF being minus 5. How do we interpret that? It really means the source actually has the opposite polarity that we are showing. So given all the other conditions in the circuit that we've been given, there's no possible way to have this EMF oriented the way it is. It has to be the opposite polarity of size 5 volts. Okay, you ready for a more challenging circuit to analyze? This one we actually need Kirchhoff's laws for. And the main reason is, because you look around here, as you look at this, you say, well, is this series or parallel? Well, it looks like parallel here, but then we got this funny thing across. And where do we go? How do we consider the current paths? Well, this makes it a little more complicated. It's a little bit indeterminate. And so Kirchhoff's laws are a perfect application here. So we're going to determine the unknown currents, VAB, voltage across here, and the equivalent resistance of the whole circuit. So let's start defining some currents. There's I1, I2, I3, I4, and I5. Now you could have chosen them differently. You could have rearranged them, put them in different directions, and I haven't proven that this is the way they're actually going. What if this is going the other way? Possibly it is. It's not always so obvious, as I already indicated. Well, we have a total current then also. So what we're concerned about is getting 5 currents, but that's really more than we want to deal with simultaneously. Too many equations to solve. So we're going to combine down to 3 currents, then produce 3 separate loop equations. And there's actually 7 possible loops in this circuit. Well, so here it's redrawn, and I'm going to reduce it down to from 5 to 3. So here's I1, like before. I1, and we have I2 over here. And we have I3 here in the middle. Now, given that this is I1 and this is I2, then the currents going into this junction, since I1 and I2 are flowing out, is simply I1 plus I2 flowing in. And now I1 goes into A, I3 goes out, and this one goes out. So I want to figure out, what is this one here? Well, it would be I1, except I3 bleeds some off. So it would be I1 minus I3 equals this one. So I1 minus I3. And in like manner, we have I2 going into B, I3 going into B. So what's this? The only choice is I2 plus I3. And now you don't see 4 and 5, do you? So we've just reduced it down to 3 loop equations. Are you paying attention to me? Or are you still trying to find the 7 loops? All right, let's get that out of the way. Loop number 1. There is a loop. Number 2. We can take this inside path. That's 2. 3. This way, over like this. 4. You can go around like that, and this way. That's 4. 5. Inside here. 6. And 7. Around this square here. There you go. Now let's move on. We need 3 loops because we have 3 unknown currents. So I'm going to choose this as loop 1. Loop 2 is going to be the entire outside. And loop 3, I'll choose this upper inner nest here. So, equation number 1. I'm going to start here, go around like this. So that is a rise of 13. Now, minus 1I1 minus 1 times I1 minus I3, because that's what this current is, times 1 ohm, equals 0. So there's equation 1. Equation 2, around the whole thing. We have 13 volts minus 1I2, and then we encounter I2 plus I3. So minus 2 times I2 plus I3 equals 0. And equation 3, that inner nest. So starting at A and going around, we go against the current, so that's a rise in potential. So it's plus 1 I1, and then minus 1 I2, and coming around here again, we're going against the current, so it's plus 1 I3 equals 0. It's a complete loop. Now, we get this equation, and that immediately lends itself to solving for I2. I2 is I1 plus I3. All right, so now that we know what I2 is, we can eliminate that. And we just have I1 and I3. We just have 2 equations to solve. So let's do 1 and 2. Substituting I1 plus I3 for I2. So, equation 1, 13 minus I1, 1I1, minus 1I1, plus 1I3 equals 0. Wonderful. How about the next one? So 13 minus 1I2, but I2 is I1 and I3, so minus I1 minus I3, and then minus 2I2, so that's minus 2I1 minus 2I3, and then minus 2I3 again equals 0. So there's our 2 equations with just 2 unknowns, and we're almost ready to be done with this solution. Okay, simplifying those 2 equations down, there they are. Now we look at them and say, I want to add them or subtract them or do something to get rid of one of the variables. Well, there's different options. You can do something with I1 or I3. I'm going to multiply this one by 5 so that this becomes 5I3 added with negative 5 makes it go away. That's a nice simple thing to do. There it is. Put the other one as it was. When we add them, we get 78 minus 13i equals 0. The I3s go away. And so I1 is 6 amps. Let's Substitute that back in for the other equation. And we get 13 minus 3 times 6 minus 5I3 equals 0. And I3, negative 1 amps. Negative 1 amps. What does that mean? That means the assumed direction I had for I3, which was from left to right, or to the right across here, is wrong. It's actually going the other way. It's going to the left. That's the actual direction of current. No problem. All right, now I2 is I1 plus I3. There it is. Now notice, just because I3 really is going the other way, I didn't like say, oh, so I1 plus I3 is really 6 plus 1, which is 7. No, you got to stay consistent with how you analyze this all the way through. There's the total current. I1 plus I2 is 11 amps. And now VAB. VAB is I3R3, that's the voltage across there, minus 1 volt. So the voltage of A from the point of view of B was over on the right-hand side. Looking at A looks like it's at a lower potential because the current was flowing this way. So on the right side of R3, it's a higher potential than the left side of R3. And finally, our total, EMF over I, 13 over 11, 1.2 ohms. And we've just done a pretty good analysis of that circuit, and we tamed it a little bit. We showed it who's boss. We dominated it.